So I'm super excited to be here. And the very first thing I wanted to do was to acknowledge that this work that I'll be sharing with you is a serious team effort by everyone on this slide. I want to offer a special shout out to all 4 co-first authors on this work for their fearless leadership: Dan Baer, Eli Wang, Damian Merza, and Felix Binder. And a very, very special thanks to the co-PI major creative driver behind this work, Dan Yeamans. And my name is Judy Fan. I'm a cognitive scientist at UC San Diego, and I am really happy to be here and tell you about fission. So imagine that you're in a kitchen. Each of the objects that you push, lift, and pour behaves in ways that are characteristic of their physical properties: mass, shape, friction, elasticity, and so on. Although you and I might take for granted our ability to interact with the physical world around us, we as humans do have exquisitely well-calibrated understanding of how the physical world works, an understanding that we can leverage to achieve our goals, including making amazing pizza. And a major goal that many of us here share is to develop AI systems that interact with the physical world as effectively as we do. But how would we know if an algorithm understood commonplace physics in a human-like way? And if it didn't, how could we hone in on the critical missing ingredients? What we need is a benchmark that first exposes understanding of how objects will behave over time. Second, covers a wide range of different physical phenomena. And critically, does so in rich and realistic environments that we think would transfer to the real world. Now, there are already several data sets out there that probe physical understanding to at least some extent, but they all fall short on at least one of these key dimensions. So at NeurIPS last year, we introduced a new data set, which we call fission, that meets all 3 of these criteria. And the goal of my talk today is to tell you, first, what fission is and what we learned by using it. Next, I'll show you some tools that our team has developed to make it easier for you to use fission in your own work. And finally, I'll close by sharing with you where we're headed next, towards tackling some of the major outstanding challenges at the intersection of computer vision, AI, and cognitive science. So in our first fission paper, we made 3 contributions: a new benchmark data set containing diverse and realistic physical scenarios with complex object interactions. We proposed a unified evaluation protocol to evaluate physical understanding in models and humans. And we conducted systematic comparison of state-of-the-art models against human performance. The current release of fission consists of movie clips featuring a wide range of physical phenomena across 8 scenario types. In this work, we prioritize the foundational physical concepts that have previously been studied in cognitive science. So beginning with maybe one of the most widely used scenario types in studies of human physical prediction in 3D environments, it makes use of towers, of precariously stacked blocks. These are scenarios we call support. These support scenarios are interesting because they probe understanding of physical stability, an abstract property of scenes that relies on understanding of how gravity and other forces act on objects. And then as part of fission, we procedurally generated a large number of these scenarios using the 3D world simulator with different numbers of objects, different forces, and a variety of different visual contexts with large variation in textures and backgrounds. The collide scenarios focus on projectile motion and collisions between 2 primary objects. In contained scenarios, you have to understand how well one object can contain another. In drop, the dynamics depend on how objects fall and bounce off one another. Then there's link, in which objects' motion is weakly or strongly constrained by attachment to other objects. Roll and slide emphasizes the difference between rolling and sliding as a function of object shape. It also included dominoes, which measures understanding of spatial relations, momentum, and sequences of multiple collisions. And finally, drape includes cloth-like objects interacting with rigid objects under the effects of gravity. Now, with such a wide variety of scenario classes, it's not immediately obvious how to specify a task that is both well-defined across all of them and also natural for people to do, meaning the kinds of everyday physical prediction that's most relevant to human observers. And if you focus on only a single physical domain, like block towers, there may be one especially salient property, such as their stability, and you can conduct all of your evaluations just using that one concept. But if you're looking at a ball about to roll down a ramp, being asked to judge whether the scenario is stable or not is a lot less informative about the specific dynamics of this scene. It's also worth specifying a physical prediction task that's actually natural for people to do, that they can easily understand and are capable of performing. While pixel level next frame generation is generic, it is not at the appropriate level of abstraction to be a viable behavioral output for humans. On the other hand, eliciting high-level event-based predictions is natural for people to do and report on. So to meet those two conditions, we developed the object contact prediction task. The object contact prediction task, or the OCP task, asked an agent to consider two objects with a special status, the agent and the patient, and then make a prediction based on the presence and kind of other objects and forces there are in the scene as to whether the agent will make contact with the patient. Now, what's appealing about this task is that by varying those other objects and forces, it requires agents to accurately forecast how the various objects in the scene will physically interact with each other in a generic way. At the same time, the final judgment concerns whether a specific event will occur, making it a really natural way to probe human physical scene understanding. So here's what the task looked like to the human participants we recruited in order to provide a benchmark against which we could rigorously evaluate state-of-the-art models. The agent and patient objects were always pre-queued at the beginning of each trial, the flashing red and yellow masks, but otherwise were visually indistinguishable from the other objects in the scene. And then after the first few frames, and well before any objects could even come into contact with the agent, people were asked to predict whether the key contact event would occur. Then for each of 150 videos in a given scenario type, we collected predictions from 100 different human participants. In parallel, we elicited predictions from 11 state-of-the-art models on exactly the same set of videos. And because these scenarios were procedurally generated in 3D world, these predictions could then be compared to the ground truth future states of the scene, allowing us to compute objective measures of performance for both humans and machine agents. We collected these predictions in parallel for all 8 scenarios in our data set. To be clear, this was a Herculean effort for our team, and these human experiments were led by Felix Binder. So our next challenge was to develop a unified framework for training and evaluating physical understanding across models with vastly different architectures. We conceptualize each model as consisting of 3 modules. First, an encoder that takes an input, in the standard case, a series of RGB frames making up a video. The output of that encoder module feeds into a dynamics module that tries to predict the evolution of the state beyond the input frames. Note that the architecture of the dynamics module will vary depending on the format of the late representation passed in by the encoder. For object-centric encoders, these were RNNs operating over graph-based representations of special relevance to this tutorial. But for non-object-centric encoders, these were standard RNNs operating over tensor representations. And while all of our key vision model baselines operated directly over raw video inputs, we also included a particle input bypass into the dynamic modules. The reason why these particle input models are especially important and useful for our experiments is that even though we are primarily interested in physical prediction from vision in this work, we are really interested as researchers to disentangle limitations due to the encoder from limitations due to downstream modules, including the dynamics one. The third and final component was a readout module, mapping the latent representation to a prediction about the scenario. So in this case, will the agent touch the patient? And then with this generic evaluation framework in hand, we surveyed the recent literature to obtain a diverse sample of publicly available models that each represented plausible hypotheses about how to achieve generalized physical prediction. Now, we knew we couldn't conduct a comprehensive evaluation in this work, but we did prioritize including models that span a wide range of different architectures, from more generic vision-based models like SVG to architectures with stronger object-centric inductive biases, such as OP3, DPI, GNS, and RPIN. We also made sure to include models that varied in how they were trained. Some were supervised with ground truth object metadata, like RPIN, and others self-supervised on pixel reconstruction, like SVG. And we obtained several key results based on our parallel evaluations of models and people. So here I'm going to plot accuracy on the test set videos on the y-axis and all of the agents along the x-axis marching from left to right. But before we go there, I want to mention that this work was the product of joint leadership by Eli Wang and Dan Baer with key contributions from Damien Mirza. So our first observation was that humans are good, but they are far from perfect at making predictions over these scenarios, averaging about 75% correct predictions. But as you can see with the little grayed out icons on this plot, there was also substantial variation across different scenario types. And given our sample size, we can be fairly sure that these estimates are highly reliable. Our second observation was that none of the computer vision models that we tested came close to human performance. Though some of these were significantly better than others, here the blue group over the red, models that received supervised or unsupervised training signals related to objects rather than simply predicting the future pixels of a movie seemed to achieve higher accuracy, which suggested to us that explicitly abstracting away from the pixel level may be really important for tasks like natural physical scene understanding. And that observation is consistent with another really key result from our experiments. Algorithms that take particle-based object meshes as input approach human-level performance. Of course, these models solve a much easier problem than humans. They don't have to infer anything about physical state from visual inputs, but already have a rich, explicit, accurate scene description given to them directly. And since our goal was to identify candidate models that could not only perform well, but also behave in a human-like way, we also computed a measure of human model consistency, which I'm plotting on the right-hand side of the slide. This tracks how similar the pattern of errors that were made by each model by comparison with the amount of variation within our human sample. So this analysis revealed a striking correspondence between performance, absolute performance, and consistency with humans. In other words, models that approached human-level performance also made more human-like predictions. However, while some of the particle input models achieved human-level accuracy, there remains a significant gap to close in order to achieve human-like physical prediction, as indicated by the flatter slope of the purple curve on the right. And taken together, these results suggest that a model's latent scene representation is critical to its prediction ability. And we think then that a crucial open problem in physical understanding is building models that learn to abstract out an explicit physical scene representation, perhaps a scene graph, from pixel inputs. Okay, so far I've told you about what problem the Fission dataset and benchmark was designed to solve, and some of the preliminary insights that we've gained from conducting evaluations of current models and benchmarking them against human behavior. But I'm here at this tutorial to tell you that the evaluations we've done so far are just scratching the surface. Our real hope for Fission is that it'll be a useful resource for the computer vision community here and AI community more broadly to help you and your colleagues benchmark your own or others' models and understand how well they are approximating human physical prediction. Okay, so here are some pointers to publicly accessible resources that we've created to first remind you of key details about Fission and our main findings. We have a short blog post on our project website, as well as one of our GitHub repos where you can easily download the full data set, including all videos and ground truth metadata about every 3D scenario at all time points. And then third, another repo containing the code we use to evaluate the models in our first paper, as well as some starter code to help you evaluate new models. So this is a quick scroll through of that site, so you'll know that you come to the right place. It has lots of different key details here, as well as additional example videos if you scroll down to the bottom, so you can get a better sense of the array of different physical interactions that are probed in our data set. And if you visit our first repo, this contains the links to download what we're calling Fission Test Core, which is all of the MP4s that you'd need to take a look at and see the raw inputs that we use to evaluate the models in the paper, but also that you're free to use however you wish. And if you follow some of the links to a second repo, this contains the code that we use to evaluate the models in our paper, and also some additional resources for others. And if you go ahead and check out our code base and have feedback or questions, feel free to post an issue or get in touch with me or any other members of the team, and we'd be happy to try to help you get through any of the areas where there could be friction. And also mention that these resources were initially developed by Eli Wang as part of his PhD work, now at Tesla, and they're currently being maintained by Rahul Venkatesh, a new member of the Fission team. Okay, so how can you use Fission in your own work? Of course, download our data set and our model training evaluation code to test your own or others' models. Okay, finally, where do we go from here? Now, something that I left out from the earlier story is that there is a major open question raised by Fission that is of fundamental importance for understanding human visual intelligence. What is the role of forward simulation in explaining human physical prediction? So while there has been a lot of support for the hypothesis that people do use some kind of mental simulation in order to predict how states of the world will evolve over time, running a genuine internal model, a genuine world model to imagine future states, this hypothesis has actually been hotly contested in the field, with some arguing that approximate heuristics play a much larger role. These kind of shortcuts play a much larger role for explaining most everyday intuitive physical judgments. You can see some of the pointers to some of the work that's debated this issue. And as part of our Fission evaluations, we took a stab at this very question by asking how much better models did when they generated their predictions based on the output of an internal simulation process modeled by the dynamics module, versus when they only base their readout on the latent representation for the initial input frames without any additional simulation of future states. So for SVG on this plot, that would be the difference between the circle and the square. And we actually don't see an advantage for using the output of simulation relative to just using the initial frames. And SVG was not the exception. We didn't see a simulation-based advantage for any of the other vision models we tested. But critically, we do see a boost when these models are shown the full movies, indicating that these features are useful for exploiting features of the input to detect object contact events, even if they don't support strong prediction. But these results also raise the possibility that the main way that these vision models are able to get off of chance is driven by the visual features available from the initial frames of the video, like object position, shape, and contact relationships that basically gave away what the final outcome would be. And to some extent, those kinds of shortcuts may be unavoidable for the types of rigid body scenarios that we tested, however diverse they were. So our next step is to upgrade fission in various ways. And this new release will at a minimum contain scenarios featuring variation in latent physical properties that cannot be directly inferred from a single frame, but only by tracking how objects interact over time, including variation in a much broader array of non-rigid materials, including bounciness, as demonstrated here. And here's some more early demos from Vision 2.0, which will include greater variation in mass, friction, viscosity, bounciness, again, deformability, and more. We're also very welcome to taking ideas for additional physical properties that you think would be really useful to have as part of this more comprehensive benchmark. This new work is being led by Fish Tung, a postdoc on our team. Vision 2.0, in addition to including more materials and be more challenging for physical understanding in that way, will also generalize beyond the base OCP task to include large-scale human psychophysical measurements of other aspects of human scene understanding, including uncertainty, providing an even richer target for models to capture. And the final idea I'd like to leave you all with is that you can think of fission as just one instantiation of a larger enterprise that my collaborators and I call cognitive AI benchmarking, or CAB for short. CAB is not business as usual in AI or in cognitive science. It brings together the study of human cognition with the design of new algorithms and the engineering of realistic virtual environments in a virtuous cycle. And this is the kind of multidisciplinary teamwork that we think will really pay off in the long run. And in short, CAB, what distinguishes CAB is that it aims to conduct rigorous measurements of natural human behaviors. Think exploration, communication, collaboration, planning in realistic environments in order to reveal the size and shape of AI human gaps today. And thus, the opportunities, the specific opportunities for next generation AI systems to fill. Okay, with that, the end, and thank everyone else on the Fission team once more, as well as our generous sources of funding. Thank you.